Good afternoon, dear student, and welcome to this ninth session of our Numerical Method 2 class. Without any further ado, let's dive directly into what we saw yesterday. So we tackled, before we parted yesterday, we introduced the notion of Chebyshev polynomial. And the motivation behind was the least square method. Remember that in the least square method, you want to, and for the purpose of the least square method is to fit a particular function to a set of data points. And the structure of the function that you fit can be generalized because in general you use polynomial, right? You can use a polynomial or you can use trigonometric polynomial. Meaning that it's a combination or linear combination of sine and cosine. So you can use trigonometric polynomial, you can use polynomial, and you can use other form of function. But the functions are in such a way that you are in a certain space in which you have a basis, and then you take a function as a linear combination of the basis, right? Now, when you say linear combination, it means that you have sum with weights. Those weights, we denoted them by Ci, the coefficient, right? When you write linear combination, you have coefficient, right? Okay, now in the least square method, the purpose is to find those coefficients, right? In such a way that the error is minimized. So when we apply the least square method, we obtain a minimization problem, which gives us what we call Normal's equation. And Normal's equation are linear system that we solve. And an efficient way to solve the normal equation or the associated linear system is to select the basis in such a way that the coefficient matrix is identity or close to identity or a factor of identity. Because if you have such a simplification, then it becomes very easy for you to compute the coefficient Ci. Okay, we saw that in order for the linear system to be identity or close to identity, we need the basis to be orthogonal. And we define what is an orthogonal function. Obviously, orthogonal function is an orthogonal function when the element are selected in a finite space, or you have a finite number of points. Then you can map this to Rn or Rn plus 1, something like that. Okay, now let me share that screen with you and I will explain something that I didn't explain yesterday. Okay. Okay. I see that I didn't share any slide. Okay, let's start with this. Okay, so you can see here, this is where we define the orthogonality property. Right, you can see here. Now, if you look at the summation here, you can see that k is run from 0 to m, and k is what? Xk. So here, you take a finite number of points, xk, to define orthogonality. And you take a finite number of xk. Okay, so let me explain what I want. What I want to do now. I want to show to you that this is equivalent to the dot product. That's just what I want you to see. And for that, let me open a new slide. A new slide. Okay, we have this. This is our basis. Basis of a vector space. Okay, we can denote it even by G, but that's not important. Now, this is what we call the orthogonality property. Okay, this is what we call the Kronecker delta function. And it takes only two values, 0 or 1. So it takes the value 1 when I is equal to j, when the two indices are equal, or 0 if they are different. So this is called Kronecker delta function. So this is what we call orthonormality. Orthogonal is this one. Here is orthogonality, and this is the normality. And if both are satisfied, we say this is orthonormal, right? So this is the orthogonality. And this one is the normality. That is, the norm is 1. All right. Now, this, you can see we can write this as, we can write this one. So this is like sum okay, this is like a vector x I k times y or xj, but let me give them two names, right? Of course, I put I here to say that, of course, it's subscripted here. I can give a different name, it doesn't matter. K. So you see that here we have the component. So I can call xi, because these are the component of xi. Oh, so xi is xi1 up to xim. Similarly for that one, right? Similarly for the other one. So this one, I can call it so you agree with me that if I compute the dot product of these two, I will compute this times that and so forth. So that's exactly what we have here. Okay, now what is our what are these components? These components are just these ones, right? So I can write that my xi, I can say that xi is the same as what? Gi. Right. Now, if I want a component, I just apply it at the point, right? At this point, xk. So if I apply that, because it has that number of components, xi k is just this. Right. So for k equal to 1, I have this one, k equal to 2, next one, up to k equal to m, I have that. So you can see that this is a dot product in what? In Rm. Oh, okay, start from 0 here. So from 0. So you can see that this is a dot product in Rm plus 1, because in total we have from 0 to n, we have m plus 1 subscript. So this is in fact a dot product in Rn plus 1. Meaning that the vector has m plus 1 component. Okay, that's the remark I wanted to make so that things will be clear to you. You know what is a dot product? You have two vectors, dot product. When the dot product is 0, you say that the two vectors are orthogonal. That's what you have here. Okay, but you can see that this one and that one, when I is equal to j, then this will give us the norm of the vector itself, right? Because you have the vector dotted with itself, it will give you the norm square. So if the norm square of the vector is 1, it means that the norm is 1. We call it a unique vector, right? And that property is what we say, normality, meaning that the norm is 1. Okay, now let us continue with our class. We define what we call Chebyshev function of the first kind, polynomial of the first kind. Chebyshev polynomial of the first kind. Chebyshev polynomial. Of the first kind. So we said by definition, Tm or n, whatever you put there, is cosine m cosine inverse x. So this is how we define for m. If I change this, I change there, right? So that's how we define it, and I say that this is a polynomial of degree n. Of course, it's a polynomial of degree n. We computed a few of them, and you could see that indeed they are polynomial. Okay, is that clear for everybody? Is it clear? Okay, so now we proceed. Now I'm going to show, I'm going to prove some of the properties. We have the following property. I'm performing a surgery here. This is a surgery, live. You don't need to go to the hospital to see. You can see it live and in concert. A live concert. All right. Our Kashopi, I hope you are not impressed. Okay, so we are going to write our recursion formula. The recursion formula, we are going to write Tn plus 1 in terms of the preceding, right? In terms of the previous two terms. The two previous terms, that is Tn and Tn minus 1. So how do we do that? So we have Tn plus 1 of x is equal to 2x Tnx minus Tn minus 1x. So that's the property, and it comes from a trigonometric identity. So this results from the trigonometric identity. Okay, so this is our recursion formula. So it comes from this trigonometric. If I take cosine n plus 1 of whatsoever theta or x, okay, we have cosine here, right? I can put this or x, it doesn't matter. I hope it doesn't hurt anybody. Who is hurt if I put x instead of theta? Who will be hurt? Okay, nobody. Good. So plus cosine n minus 1 theta whatsoever. So this is nothing else than 2 cosine theta cosine n theta. And you can see that this is, if I put 0 here, no, if I take this to be 1, if I take this to be 1, this is our theta. You can call this theta. You can just put theta there. It's an angle, right? Theta is an angle. Now you see, if I take t equal to 1 here, I put 1 there, it will be cosine theta, right? So that will be this one, cosine theta. But what is cosine theta? Remember that after this, I have theta is what? Cosine inverse x. Now, if I apply cos theta on both sides, this implies that cos here and cos there. So cos theta is x, right? So from this, cos theta is x, right? So this will be x. Okay, and now this one is by definition, this is Tn, right? Because if this is m, n inside, so this will be Tn. Put Tn there, right? And this is Tn plus 1, Tn minus 1. Okay, so I replace. So this gives us, for this one, this is Tn plus 1 x. I've got this is x plus Tn minus 1 x equal to 2x cos theta x, and this one is Tn x. Right, now I can take this to the left-hand side, and we obtain this, right? So if I take that to that side, we obtain that. You see, so that's the recursion formula. And now from this recursion formula, you can see that Tn is of degree n. Just do that by recursion. So if you take, I already said, if n is equal to 0, from the definition, from this definition, for n equal to 0, Tnx is equal to T0x. And what is T0x? It's equal to cosine of 0 times theta, whatever is there, which is cosine of 0, and cosine of 0 is 1. So you can see already that for for n equal to 0, T0x is 1. Now, when n is equal to 1, we saw that T1x is cosine 1 into cos inverse x, right? So cos into cos inverse x So if I have a function composed with its inverse, is the same as the inverse composed with the function. It gives identity. So if I apply x here, x there, identity into x is x, right? So this is x. Okay, so that's for n equal to 1. Now, if n is equal to 2, you agree with me, eh? If you are not happy, raise your finger. Now, if you take n equal to 2, I substitute into this. Let me call that star, into star. So this is star. So if I substitute into star n equal to 1, so if I take into star, I just substitute n equal to 1 here. 1 plus 1 will be 2. So for n equal to 2, I substitute 1 here. Then I have T2. X will be what? 2x into T1x minus T0x. So if I substitute, we know that T1x is x, so it will be 2x into x squared minus T0 is 1. So what is the value of n here? N is 2, the degree is 2. N is 1 here, the degree is 1. n is 0, you can see it's a constant term, so the degree is 0. Now, similarly for n equal to 3, now T3x will be 2 T2x minus T1x. But we have just computed T2x, which is this one. So we just substitute. So that would be 2x into 2x squared minus 1 minus this one, which is x. So if we expand that, so if we expand, it gives us 4x cubed minus 3x so you can see that n is 3, the degree is 3. So you can, by recursion, you can assume that the degree of this, okay, you can use proof by induction. If you use proof by induction, you'll be able to prove that this one is of degree. I hope you understand what I mean. If you assume that this is k minus 1, you assume that it's true for a fixed k. That when n is equal to k, the degree is tk. Sorry, the degree of tk is k, right? Then you come there, you take this to be tk plus 1. Then you have tk here, polynomial of degree k. Now, if you multiply a polynomial of degree k by x, it becomes k plus 1. And that is it. So you can do that by induction. Okay, so you can do that. Okay, there's a remark. If you look at the remark, you will see that when, okay, let me do the other one, right, before I make my point. Now, if you take n equal to 4 here, you can do the same thing. T4x will be 2x into T3 minus T2x. But what is T3? T3 is this one, so you just substitute 4x cubed minus 3x minus 2x squared minus 1. Now, if you expand this, oh, this thing wants me to lose my temper, but I don't want. Okay, let me perform. Hey, where's Joe? I haven't seen Joe since the beginning of the semester. Joe, is she there? Okay, so how come I forgot about Joe, my friend Joe? Okay, now if you expand this, you can see that this will be 8x4, right? Now, this will be negative 6 minus that one is negative 8x. 8x squared, right? That's negative. Now, The last one will be plus 1. Okay, so the remark that I wanted to make here is that when n is an even number, when n is an even number, you can see like this and that one, you have a constant term at the end. For all the polynomial, you get this constant term. Not necessarily 1, but it will be a constant term, right? You have a constant term here. But when it's even, if it is even, you will see, sorry, when it's odd, I already said even here. When this is even, you have that constant term. But when it's odd, like here, you see that it's only in x. There's no constant term. You can also see here. Everything is in x. There's no constant term. So you can, even here, okay, this one is 0, right? That's 0, it doesn't count. Okay, so that is it. That will always be the case. And something else is that the leading coefficient of Tn, of Tk, Tn, T whatsoever, the leading coefficient of Tn, x, because we know that this is a polynomial of degree n, the leading coefficient will be 2 to the n minus 1 into x. So this will be the leading, oh, sorry, n to the n, this one. This is the leading term. Okay, those are small remarks, right? Okay. Okay. Now the orthogonality property. I define this one like a dot product if you want, but inner product, dot product. This one. So if I have m, n, so we can define this. It's a form of dot product, right? Or inner product, dot product. So it's a dot product. So we take here Tmx, Tnx, dx by one square root of one minus x squared. Right. Okay, so this is how we define the dot product. The dot product, right, of okay, so what I want to do now is to show, no, I don't think I have to show to you how to get the results of that integral. Okay, I will just give you hints, right? I will give you hints. Let me quickly go to that. Should I give you some hints? Should I give you some hints? Okay, the limit here is from -1 to 1, right? Because this one, Tnx is defined. Okay, so how do we know that x is between? When you see, look here, this is x is cosine. I hope you all see the cursor here. Okay, here. This is cosine x is x. And we know that cosine is between -1 and 1, right? So it comes from there. X is always, this x is always, you can write it as cosine of theta. And this theta is not taken to be the entire real line, because we want see this definition, cosine inverse of x. You see that we are defining the inverse of cosine. So actually cosine itself is not invertible because it's oscillate like this. So cosine is not a monotonic function. Because for a function to be invertible, it has to be monotonic. Monotonic, increasing or decreasing, that it doesn't matter. It has to be monotonic. Right. It has to be monotonic. But since the function on the real line oscillates, so it will be monotonic, increasing and decreasing. I mean, the interval that was selected was the interval from 0. If you sketch the graph of cosine, okay, let me sketch the graph, because this definition shows that the function is invertible in a certain interval. Yeah. Yeah. So you have to select the interval where cosine is invertible before you define the inverse. Right. Okay. Now, let me draw the. Ooh, time is running, eh? Ooh. But anyway, it's important to do that. Okay. So this is our unit circle. Okay, so we assume that this is 1 and this is -1. All right, and this is 0. Okay, cosine from 0 at 0 it is 1. We know that. Okay, if you don't know, I'm informing you. I know it. So I know that it is 1. So it will go like this. It will decrease. And there, and then it will continue like this. You see. And here you have a local minimum. Where it's -1. And where it's -1 is pi. The value there is pi. Because cosine at pi is -1. At 0 is that, right? And this is pi by 2, the middle. So this is pi by 2. And here this is pi and this is 0. Now you can see that from 0 to pi, my function is decreasing. You can see. Now if I proceed there, it will be increasing. So you don't take that interval. So this is the interval where you define, where cosine is defined. Where you restrict and define the inverse. Or when you say arc cosine or cosine inverse, it is on this interval from 0 to pi. So we take this, the function is invertible, so cosine is invertible in this interval. So cosine, so if I define the cosine function from this interval, from 0 to pi, here. Obviously, I can put r there, but you see that it will take only the value from -1 to 1. That would be the range, -1 to 1. So this cosine is invertible. I repeat that it's not invertible if you take from r here. If you take the whole real line, it will not be invertible. You just need this portion, this one, from 0 to pi to define the inverse here. All right? Now you can see that if you take this function, because it's invertible here, now the inverse is what we call arc cosine or cosine inverse. So that inverse is defined from this interval to that one. So the inverse cosine inverse is defined from from 0 pi. Okay, so you see that if I take my x, if I take my x here, like tx, remember that when you say t n x, it is equal to cosine n, and then you have cosine inverse of that x. Oh. Cosine inverse of that, you see that this cosine inverse, this x is that in that interval -1, 1. And that's why we have here, -1, 1. Okay, now in order now to prove the orthogonality property, do you have a class? Normally it's in 1 minute it will be time. Do you have a class after this?
No, sir.
Huh?
Yes, let's do. Yes, sir.
You have a class.
Yes.
Okay, please, we can stop here. We can stop here. Yeah, we can stop here, but I will continue. You will watch it in the. I will not really continue. I just want to substitute this expression. Okay, okay. Let's stop here. But I hope this explanation, through this explanation, you understand why we are talking about the inverse of the cosine. Cosine itself is not invertible, but when you restrict it in a particular interval, it becomes invertible, and it's only on that interval. So each time you are dealing with this inverse of trigonometric function, make sure that you understand what it means. Right? Are only invertible in a subinterval where they are defined. That's where you define arc inverse, that is arc, cosine, arc sine, arc tan, all those functions, trigonometric functions. It's in a given interval that you restrict and you define the inverse there. Okay, thank you for your kind attention. God bless you and see you tomorrow. Yeah, tomorrow. Bye-bye. Some people are sitting there. You told me that you have a class. Okay.